Hi guys, in this video we will continue learning about pressure. Why the variation of pressure with depth matters. Pressure in a fluid at rest does not change horizontally. However, this is not the case in the vertical direction in a gravity field. Pressure in a fluid increases with depth because the effect of extra weight on a deeper layer is balanced by increased pressure, as shown in the given figure. To obtain a relation for the variation of pressure with depth, let us consider a rectangular fluid element of height delta z, length delta x, and unit depth delta y in equilibrium. Assuming the fluid's density is constant, a force balance in the vertical z direction is given in a presented equation. Where a capital W is the fluid element's weight, delta Z is the difference between Z2 and Z1. The symbolic terms of M, a capital V, and G are defined in the illustrated bubble. Based on this equation, the final unit of weight is the Newton. If the equation is divided by delta x and delta y and rearrange it, yields as the following form. Thus, we could conclude that the pressure difference between 2 points in a constant density fluid is proportional to the vertical distance delta z between the points and the fluid's density. The negative sign denotes that the pressure in a static fluid increases linearly in depth. For a given fluid, the vertical distance delta z is sometimes used to measure pressure, and it is called the pressure head. A more straightforward equation to remember and apply between any 2 points in the same fluid under hydrostatic conditions is given in the following form. Where the hydrostatic condition is defined as fluids at rest and the pressure in a fluid or exerted by a fluid on an immersed body. Below refers to the point at a lower elevation and above refers to the point at a higher elevation. If we take the above point to be at the free surface of a liquid open to the atmosphere, as shown, where the pressure is the atmospheric pressure, then the pressure at a depth h below the free surface becomes as in a given expression. Pressure in a fluid at rest is independent of the shape or the cross-section of the container. This principle depicted in the figure. It changes with the vertical distance, but remains constant in other directions. Therefore, the pressure is the same at all points on a horizontal plane in a given fluid. Note that the pressures at points A, B, C, D, E, F, and G are the same, since they are at the same depth and they are interconnected by the same static fluid. However, the pressures at points H and I are not the same since these 2 points cannot be interconnected by the same fluid, although they are at the same depth. Also notice that the fluid's pressure force is always normal to the surface at the specified points. This concept can be summarized through the given expression. What is Pascal's law? A consequence of the pressure in a remaining fluid constant in the horizontal direction is that the pressure applied to a confined fluid increases the pressure throughout by the same amount. This is called Pascal's law after Blaise Pascal. Pascal's principle is the force applied by a fluid is proportional to the surface area. This can be demonstrated through the given diagram. Based on the principle, this device enables us to lift a car easily with one arm. Noting that P1 is equal to P2 since both pistons are at the same level. The ratio of output force to input force can be determined through a given expression. The area ratio A2 over A1 is called the ideal mechanical advantage of the hydraulic lift. Now, let us review devices used to measure pressure. A barometric pressure is used to measure atmospheric pressure. Thus, the atmospheric pressure is often referred to as the barometric pressure. As shown here, a basic barometer used to measure the atmospheric pressure. The atmospheric pressure can be measured by inverting a mercury-filled tube into a mercury container that is open to the atmosphere, as shown in the given figure. If we exploded the barometer figure to split the mercury-filled tube, we could view forces that exist in it. The pressure at point B is equal to the atmospheric pressure, and the pressure at point C can be taken to be zero since there is only mercury vapor above point C and the pressure is very low relative to the atmospheric pressure and can be neglected. Writing a force balance in the vertical direction gives the following expression. Where ρ is the density of mercury, g is the local gravitational acceleration, and h is the height of the mercury column above the free surface. A frequently used pressure unit is the standard atmosphere, which is defined as the pressure produced by a column of mercury of 760 millimeters in height at 0 degrees Celsius. The mercury density is 13,595 kilograms per cubic meters under standard gravitational acceleration of 9.807 meters per square seconds. If the water instead of mercury were used to measure the standard atmospheric pressure, a water column of about 10.3 meters would be needed. In this problem, the atmospheric pressure is to be determined. The barometric reading at a location in height of mercury column is given as follows. The atmospheric pressure is calculated using the given equation, and it is 98.5 kilopascals. Now let us discuss example 1.7. In this problem, the IV fluid and the blood pressures balance each other when the bottle is at a certain height. The gauge pressure of the blood and elevation of the bottle required to maintain flow at the desired rate is to be determined. The density of the IV fluid is given to be 1020 kg per cubic meters. The schematic for example 1.7 is shown. If we could recall the previous lesson as illustrated, straight away we could use the pressure at any depth below the free surface equation to determine the blood's gauge pressure. Before we solve the problem, you should define your assumptions for simplification. As shown here, where the IV fluid is assumed incompressible and the IV bottle is believed to open to the atmosphere. The density of the IV fluid is given to be 1020 kg per cubic meters. Noting that the IV fluid and the blood pressures balance each other when the bottle is 1.2 meters above the arm level. The gauge pressure of the blood in the arm is simply equal to the gauge pressure of the IV fluid at a depth of 1.2 meters, as illustrated. provide a gauge pressure of 20 kilopascals at the arm level, the height of the surface of the IV fluid in the bottle from the arm level is again determined from the given expression. Therefore, the bottle's height at the arm level for a gauge pressure of 20 kilopascals is described here. To further understanding this topic, let us consider problem 162. In this problem, a gas in a vertical piston cylinder device is pressurized by a spring and the piston's weight. The piston has a mass of 3.2 kilograms and a cross-sectional area of 35 square centimeters. The compressed spring above the piston exerts a force of 150 newtons on the piston. The atmospheric pressure is given as 95 kilopascals. The pressure of the gas is to be determined. The schematic diagram of the piston cylinder device furnished with a spring is shown. The gas pressure inside the cylinder can be determined by carrying out the piston's vertical forces balance. Therefore, a free body diagram of the piston balancing the vertical forces is illustrated. The piston's vertical forces balance analysis yields the following answer. The pressure inside the cylinder is 147 kilopascals.